Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to use graphical methods to kind of analyze the motion of an object. In this case, we're going to take a look at the object of this little race car here. Now, for this example, we're going to look at what happens when this race car goes from 0 to 60 miles per hour in a 10-second time frame. And what we're going to do is try to calculate the distance traveled by the car and the acceleration of the car. Now, when analyzing motion, the very first thing we need to do is define a coordinate system, because position, velocity, acceleration, these are all examples of what are called vector quantities. So when you're dealing with vectors, you have to have a set of coordinates to reference to give the vectors direction. So I'm going to go ahead and put a coordinate system here. I'm going to put an XY axis right here. X, Y. Now, this is a one-dimensional problem. We really don't need the Y axis, but since most problems in physics are, the overwhelming majority are two-dimensional, I usually use a two-dimensional coordinate system. So what we're going to do is we're going to keep track of the coordinates of this car. Now, I put it right here. It doesn't really matter if it's here, here, or up or down. Just pick a spot and put the coordinate and put the axis in. I did make it so that basically the car is starting at x equals 0. Important to realize that as the car accelerates, this thing is staying put. This little dot here, the origin of this coordinate system is staying put, and the car will now move with respect to the coordinate system. All right, next, in order to help visualize what's happening, we're going to draw the motion diagram. So again, a motion diagram is like, imagine a digital camera taking snapshots in time. Click, 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 and then superimposing all of the pictures. And what we'd see is a series of automobiles here. Now, I'm not going to redraw the car over and over and over. I usually use like a dot to represent the vehicle or whatever the system is. All right, a little time later, maybe the dot might move to like here, and a little time later, maybe here, a little time later, maybe here, a little time later, maybe over here, and so forth. Now, these dots would be getting further apart because as time goes on, this car is moving faster and faster and faster. I sometimes include velocity vectors. Now, we don't have to have a whole bunch of them, but maybe the velocity of the car here is to the right. A little further on, the velocity is a little higher. A little further on in time here, the velocity is even higher yet. So these are velocity vectors, which are just graphically demonstrating or showing that the car is moving faster and faster and faster. Right now, the graphical analysis. So now what I'm going to do is draw another sketch here of velocity against time. So you've got me for physics, I'm real big on graphs. The velocity graph is the one that's basically the most useful. Once you have the velocity graph, it's just a one-step process to both position information and acceleration information. So if we were to sketch a graph of velocity against time, the car's starting at 0 mile per hour. So at t equals 0, I'm going to say the velocity is 0. That would go here on the graph. All right. After 10 seconds, the car is going 60 mile per hour. Right now, at this point, we have to realize that we've got kind of mixed units here, this hour and seconds and miles. We have to make a decision on what type of units. What I'm going to do now is I'm going to work in feet and seconds. So before I do anything else, I'm going to take this 60 mile per hour, which if I actually write it out correctly, it's mile over hours, and we're going to do a unit conversion on it. And if you haven't done a unit conversion, go back, review my video on how to convert units. I'm going to start by converting this mile to feet. And I would do that by multiplying by a conversion factor that has feet up top, miles in the bottom. Notice that the miles will cancel and leave us with feet. And then you would look up how many feet there are per mile. There's 5,280 feet in 1 mile. You could also look up how many miles per feet. Okay. Right now, if we multiply this out, the miles cancel, we're left with feet per hour. What I'm going to do is multiply by another conversion factor to convert the hours into seconds. So our next conversion factor has to have hours up top, seconds in the bottom, so that the hours will cancel. And there's 3,600 seconds in 1 hour. So when we multiply this all out, the hours cancel, the miles cancel, the hours cancel, and we're left with feet per second. And we multiply this out, I get 88 feet per second. So getting back to our graph, after 10 seconds, the car is going 60 miles per hour, which is equal to 88 feet per second. So I'm going to put this on my graph here. 10 seconds, 88's up here somewhere. 88 feet per second. Now, I'm just, basically, you can put this 10 seconds really anywhere you want when you draw your own graph. At this point, I've set a scale, though. This is 10, then 5 is about here, and 20 is about here, and so forth. Same thing vertically. It doesn't really matter where in this problem I put this dot, but at this point, I've set a scale. 44 would be about here, and maybe 120 would be up here, and so forth. If you had a graph that had hash marks already, you would probably want to honor those hash marks, or if it had a scale already, you would honor the scale and put the 10 where it belongs and put the 88 where it belongs. All right, so we've got these 2 points on the graph. Now we have to ask ourselves, how do we think these are connected? So depending on what class you're in, I talk about this in Physics 111, when cars accelerate, they do so in a way, at least at low speeds, that's approximately linear. You can try this for, yourself when you're driving down the road, or actually do it when somebody else is driving, but, when they're stopped at a stop sign and then they give it gas and watch the speedometer, particularly if they don't move the gas a whole lot with their foot, if they keep it at about one setting, you'll see that speedometer go from 0 to 10, and then from 10 to 20, and then from 20 to 30 in about the same time frame. So this graph here, I'm going to assume it's approximately linear. A little bit of an assumption. It may not be exactly linear, but that's okay. All right, so here's our velocity graph. It's good from 0, 0 to 10 and 88. Now what I'm going to do is use it to calculate the displacement. Now I know I called it d here, but really in this coordinate system what I'm calculating is the change in position, the delta x. And hopefully you've seen my videos on how to calculate displacement from a velocity graph. The displacement is going to equal the area bound under that curve. So that area is a triangle. That's going to equal 1/2. The base of the triangle is this distance, which is 10 seconds. And the height of the triangle is this distance, which is 88 feet per second. And when we multiply this out, I get 440 feet. Okay. Also notice we could have calculated it like this. Displacement, or our delta x, can be calculated by average velocity times time. And the average velocity, if we start at 0 and we end up at 88, would be 0 plus 88 over 2. In this equation, that's this stuff right here. That thing that I've kind of outlined in red, there's your average velocity times time. So average velocity times time is kind of equivalent to area under the curve. I like to use area under the curve because in a lot of problems it's difficult you won't know what the average velocity is. Here it'd be pretty easy to calculate, but in other problems it's quite a bit tougher. All right, next, let's see, acceleration. So remember, acceleration is a rate of change. It's rate that velocity changes. On the graph here, that's slope, right? It's the slope, delta v over delta t. Right, so on our graph, there's our delta v, 88 feet per second. There's our delta t, 10 seconds. So this is going to be 88 feet per second over 10 seconds, which is 8.8 feet per second per second. A lot of textbooks would like to write that 8.8 foot over second squared. These are equivalent. The foot per second and the foot over second squared are the same thing. I really like this unit for acceleration. I think it very nicely demonstrates what that acceleration is telling you. This 8.8 foot per second means, after 1 second, that car is traveling about 8.8 feet per second. And after another second goes by, it's going to increase in speed by another 8.8 feet per second. And then it'll increase in speed by another 8.8 feet per second, and so forth. So, the point of this video was how to use a velocity graph to do a simple distance and acceleration analysis of an accelerating automobile. I hope that this video helps you, demonstrate how to use these concepts. Have a great day.